Welcome back, everyone. Today we're going on a deep dive into something pretty familiar, I think.
Yeah, the lemon battery.
Exactly. Sticking some metal into a lemon and getting a little bit of electricity.
Mm-hmm.
But we're going to go a little deeper than that today. We're going to explore the history of it, the chemistry behind it, and even how it shows up in pop culture sometimes.
Right, and it often a first step for many STEM students into electrochemistry, but there really is a lot more to it than you might expect.
So let's start off with that history. Our sources indicate that it's actually got a connection back to Alessandro Volta's first electric battery back in 1800.
Well, Volta didn't use lemons. He used brine, a saltwater solution, for his electrolyte. But the principle is the same.
It's all about chemical reaction.
Right, generating electricity through those reactions. And both Volta's invention and the lemon battery leverage what we call oxidation-reduction reactions.
Redox reactions for short. But for our listener, could you break that down a bit? What is a redox reaction?
Sure. Basically, it's when electrons are transferred between two substances. One loses electrons, which is oxidation. The other gains electrons, which is reduction. And that exchange is what drives the current.
So how does that work specifically in the lemon battery?
Well, the zinc electrode acts as what we call the anode, and that's where the oxidation happens. So the zinc atoms are losing electrons and dissolving into the lemon juice, which is acidic, as positively charged zinc ions.
So the zinc is kind of like sacrificing itself to create this current.
You could think of it that way.
Yeah.
Then those electrons that are freed up from the zinc, they flow through the circuit.
To power whatever's connected.
Yeah, and they end up going to the copper electrode, which serves as the cathode.
And that's where the reduction happens.
Exactly. At the copper cathode, the hydrogen ions from the acidic lemon juice, they gain those electrons and form hydrogen gas.
Oh, so that's why you see those little bubbles forming on the copper.
Precisely.
So the lemon juice is crucial here because it's the electrolyte, right? The bridge between the two reactions.
That's right. It lets those charged particles move around, and that's what creates the flow of current.
Now our sources talk about how lemon batteries are really popular in education.
Yeah. They're great for hands-on learning.
Yeah.
Students can play around with different fruits and vegetables as the electrolyte, use different metals for the electrodes, and see how that affects the voltage.
I've even seen them connecting multiple lemon cells together to increase the voltage.
Yeah, you connect the positive terminal of one to the negative of another, and you can add the voltages together.
To power something like an LED.
Right, or even a digital clock sometimes.
That's pretty cool.
Yeah.
It's interesting. The sources mentioned you usually need at least 2 lemon cells in series to power something like that.
Right, with the standard zinc and copper electrodes.
But they say if you swap out the zinc for magnesium, then just one cell can do it.
Yeah, because magnesium has a higher, what we call electrode potential than zinc.
Meaning?
It means it's more likely to lose those electrons, and so you get a higher voltage, around 1.5 to 1.6 volts with magnesium.
So you really can make a difference with what materials you use.
Absolutely. Even small changes can have a big impact on how the battery performs.
Now let's talk about some of those variations.
Okay.
You don't actually have to use a lemon, right?
Nope. Lots of fruits and vegetables work.
Mm.
Each one's going to have a different acidity, different pH level, which affects the output.
Mm.
One interesting one is boiled potatoes.
Boiled potatoes?
Yeah, they've actually been shown to produce more electricity, and there are even commercial potato clock kits that use them.
Why would boiling a potato make it better?
When you boil a potato, it breaks down the starch molecules, and that releases more ions, which improves the conductivity.
Oh, so it's not just about the acidity, but how many ions are in there?
Exactly. And it doesn't stop there. You can even use things like vinegar or sauerkraut.
Anything acidic
Yeah.
will do the trick. And then, of course, you can switch out the metals, too, not just zinc and copper.
Yeah, you can experiment with lead, iron, or like we said, magnesium. And they all give you different voltages.
So many possibilities with such a simple setup.
Yeah. And it all comes down to those fundamental principles of electrochemistry.
Well, let's get to the heart of it then. What are the actual chemical reactions that are happening inside this lemon battery?
Okay, so let's start with the zinc electrode.
Our sources say that when you connect the circuit and current starts flowing, the zinc actually starts dissolving into the electrolyte.
Right, that's the oxidation happening. The zinc atoms lose electrons and become positively charged zinc ions, Zn2 plus Li, which then go into the electrolyte.
And what about those electrons that are coming off the zinc?
They flow through the wire to the copper electrode.
Drawn by the difference in potential.
Exactly. And then at the copper electrode, those hydrogen ions in the acidic electrolyte gain those electrons and combine to make hydrogen gas.
Okay, so that's the reduction.
Right. That's why you see those little bubbles forming on the copper.
So the zinc is basically being used up to keep the current flowing. But it's not the lemon itself that's powering things right.
Right, that's a common misconception. The energy is actually coming from the zinc. It has chemical potential energy stored in it, and as the zinc dissolves and oxidizes, it releases that energy and converts it into electrical energy.
So the lemon is just the stage for this to happen on.
You could say that. It provides the right conditions, but it's the zinc doing the real work.
Which reminds me of this historical connection our sources mentioned, the SME cell.
Ah, yes, the SME cell. It was invented in the 19th century, and it's very similar to a lemon battery.
But instead of copper, it uses a silver electrode coated in platinum.
And the reason for the platinum was to reduce something called polarization.
Meaning?
Well, polarization happens when hydrogen gas builds up on the electrode, and it starts to block the flow of current.
Oh, okay.
The rough platinum surface helps smaller hydrogen bubbles form, and they detach more easily, so you get a smoother flow of current.
So it's like a more efficient version of the lemon battery.
Yeah, it was actually used in the printing industry for a process called electrotyping.
So a simple concept like a lemon battery can lead to real technological advancements.
Absolutely.
Well, I think we've covered a good amount of ground in this first part of our dive into the lemon battery.
Yeah, we've looked at the history, the basic chemistry, and even some of the variations.
And as we move forward, we'll get into more detail, looking at some of the research that's been done, and even how the lemon battery shows up in movies and TV.
It's going to be an interesting journey. So to really see how well we understand the lemon battery, our sources point to some research done by Goodisman back in 2001. He actually tested the model of how these reactions work inside the battery.
Oh, that's pretty cool. What did he find?
Well, one thing he did was add zinc sulfate to the electrolyte.
Okay.
And when he did that, the voltage of the cell actually went down,
Interesting.
which is exactly what you'd expect based on something called the Nernst equation.
Ah, the Nernst equation. Our chemistry buffs out there will know what we're talking about.
That's right, but maybe not everyone, so.
Could you give us a quick explanation?
Sure. The Nernst equation basically says that the voltage of the cell depends on the concentrations of the reactants and the products in the reaction.
Okay.
So in simple terms, if you add more of the product, in this case zinc ions, the voltage is going to decrease.
Because you're shifting the equilibrium.
Right. You're reducing the driving force for those electrons to be transferred.
Makes sense.
Now, another interesting thing he found was that adding copper sulfate didn't do anything to the voltage.
Oh.
And that supports the idea that the copper electrode is really just there for the reduction to happen. It's not actually being consumed in the reaction.
So it's really the zinc that's doing the heavy lifting.
That's right. And he didn't stop there. Goodisman also looked at what happened to the electrodes themselves when the battery was running.
Okay, what did he see?
Well, as the battery was working, the mass of the zinc electrode decreased.
Which makes sense because it's dissolving, right?
Exactly. Those zinc atoms are becoming ions and going into the electrolyte.
So the zinc is literally being eaten away to produce that current. And what about the copper? Did anything happen there?
Yeah, he saw hydrogen gas being produced, those bubbles forming on the surface.
Just like we'd expect.
Right, because the hydrogen ions are gaining electrons from the zinc and forming that gas.
So this really confirms that whole model of how the lemon battery works.
Yeah. His experiments really backed up the theory. It's a great example of the scientific method in action.
And it's important to remember that it's not the lemon itself that's powering things right.
Right. It's easy to think that, but the energy is coming from the zinc. The zinc has this stored chemical energy, and the reaction is releasing that energy as electricity. The lemon just creates the environment for it to happen.
So it's more like a catalyst.
Exactly.
But even making the zinc in the first place takes energy, right?
And absolutely. That's
So
the
it's kind of like
point.
we're just reclaiming the energy that was put into making the zinc.
In a way, yes. It shows you how connected energy and matter are.
That's pretty cool. You know, even though it's simple, the lemon battery can get you thinking about some pretty big ideas.
Yeah, about where energy comes from and sustainability.
Before we move on to how lemon batteries show up in pop culture, is there anything else about the science behind them that we should mention?
I think it's worth pointing out that a lemon battery is never going to be super efficient. It's good for demonstrations and learning, but you're not going to power your house with it.
So why are they so limited? What are the factors holding them back?
Well, one of the biggest things is the internal resistance of a lemon battery is pretty high.
Because of the lemon juice.
Yeah, it's acidic, but It doesn't conduct electricity as well as something that's designed for a battery.
So even with more lemon cells in series, you're not going to get a lot of current.
Right. And then the reactions themselves aren't as efficient as in modern batteries. That hydrogen gas at the cathode can cause polarization.
Like we talked about earlier.
Yeah, and that makes it harder for the current to flow.
Mm.
And of course, you're also limited by how much zinc you have.
Right, gets used up.
So the battery can only last as long as there's zinc left to react.
You can't recharge it like a regular battery?
Nope, once the zinc is gone, that's it.
So lemon batteries are great for learning about the basics,
Yeah.
but that's about it.
Yeah, real batteries are much more sophisticated. We've come
Mhm.
a long way with battery technology.
It's pretty amazing what we can do now. Okay, so let's switch gears a bit and talk about something a little more fun. Our sources found that the lemon battery actually pops up in pop culture quite a bit.
Really?
Yeah, in movies, TV shows, even video games.
I guess it makes sense. It's kind of a simple visual for like a makeshift power source.
Right. For example, the villain in Portal 2, GLaDOS, is powered by a potato battery,
Oh, yeah, that's right.
which is funny because we know potatoes can actually work pretty well as electrolytes.
And there's that episode of The Big Bang Theory where they make a potato battery.
Yeah, it's simple, but people are still fascinated by it. It's like DIY science.
Right. Our sources also found lemon batteries in Red Dwarf, Bones, and Mystery Science Theater 3000.
Usually for laughs, though.
Yeah, it's become kind of a quirky science symbol.
It's funny how something so basic can end up in pop culture.
It just shows you that science can be entertaining.
Well, I think we've covered just about everything there is to say about the lemon battery. We've gone from its history and chemistry to its role in pop culture.
It's been a pretty electrifying journey.
So what are the main things you hope our listeners take away from this deep dive?
I think the big thing is that even though a lemon battery is simple, it's based on real science.
And that science has led to some really important technology.
Exactly. So understanding how it works can help you understand bigger concepts in electrochemistry and energy.
It's a good starting point.
And for anyone who wants to learn more, there's so much out there. You can look into different types of batteries, renewable energy, or even try making your own lemon batteries and experimenting with them.
That's a great idea. Well, on that note, I think we've reached the end of our journey into the world of the lemon battery.
It's been fun exploring all the different facets of it.
Thanks for listening, everyone, and we hope you'll join us again for another deep dive.